Hello, everyone. My name is Chiao. Today, I'm going to present our paper, Program Abstraction for Simulation and Testing on Smart Manufacturing Systems. We are a team from University of Illinois at Urbana-Champaign. As our title suggests, our work is focusing on the testing and the verification of smart manufacturing systems using high fidelity 3D simulators. As we know that nowadays it's a standard practice to use simulation to explore different design parameters and trade-offs. This is because the software simulators allows rapid prototyping of different designs with a much lower cost compared to real hardware. And in this in this work, we particularly study how to configure simulators with different warehouse floor plans and show its impact on the performance, such as the throughput of the system. And in this paper, we argue that the programming abstractions are required for two aspects of designing a modular and configurable simulation framework. As we know, the simulator, of course, needs to include the physical models and controllers for sensing and injecting different kinds of robot models in the system. But the simulator also should support configurations using a floor plan layout to specify the relative spatial relations between robot models. And it also requires a coordination software layer to orchestrate the controllers for each of the robots. And in this paper, we particularly focus on the floor plan and the coordination software layer aspects. Now we discuss in more details with the example systems on the right. This example system is from the Agile Robotics for Industrial Automation competition in 2021. As you already see, starting from the conveyor belt, that's where the product part enters the system, and the kitting robot arm will sort and transfer the battery to the automatic guided vehicle. The automatic guided vehicle then ship the battery to the assembly stations. And then right now you can see that the gantry robot arm then picks up this product part, in this case, the battery, and then put it in a briefcase and on the assembly table. So in this particular simulation run, the kitting robot arm has to pick up from the conveyor belt only when the battery is ready on the conveyor belt. And then they put on the AGVs only when the AGV is closed and is fully stopped. And we think that the programming abstractions for the layout and the coordination software layer is necessary in order to address this kind of challenge. So overall, the goal of this paper is to propose the following architecture. So given the particular floor plan layout and the controllers, we want to compile then to a executable simulator or executable simulation run for this particular floor plan and the controllers, and then use it to collect the statistics and analytics. And with this particular capability, we can then systematically simulate and compare different floor plan layouts, and then gradually improve the whole system based on the statistics and the analytics collected. So first, we show how the floor plan as a configuration can be specified in a configuration file, such as in JSON format. On the left, we can describe a list of robots. In this example, the kitting robot arm and the conveyor belt. And for each robot, we can specify the positions, and then as well as the operating ranges. For example, the robot arm, its range, it can move on its linear on rail from minus 4.8 to 4.8. And on the right, this is the visualization for the operating ranges and the position of the robot arm, as well as the range of the conveyor belt. And with this full layout profiles, with the relative position between all the robots, we want to construct a we call a connectivity graph. In this connectivity graph, each node is a robot in the system, and each edge in the graph represents that one robot can hand off a product part to the other robot. For example, the conveyor can hand off the product part to the kitting robot arm, and then the robot arm to the AGVs, and then the AGV to the gantry arm, so on and so forth. And so if there is a path in the graph from the source node, in this case, the conveyor belt, to the target nodes, in this case, the assembly stations, it means there is a possible route to deliver a product part from the conveyor belt to the final assembly stations. And if, for example, we modify the layout so that we increase the distance between the AGV1 to the rail of the kitting robot, and the kitting robot can no longer reach the AGV1, then the edge between the kitting robot to the AGV1 is now removed. In this case, then there's no path from the conveyor belt to AGV1. Using this connectivity graph, we can detect that the AGV1 is redundant now, because there's no way from the conveyor belt to transfer the product part to AGV1. So in general, the connectivity graph can help us filter out this we call infeasible floor plan layouts. Now we further discuss about the coordination software layer using the parameterized automata. In this work, we designed parameterized automata following our previous work, the code programming language that is used for distributed robotics applications. Roughly, we can write the parameterized automata or state machine in this extended code language. Roughly, the language feature includes how do you distinguish sensor and actuator ports from the local variables, and more importantly, the shared variables between state machines. Like the code shown in the right. And our previous work allowed us to systematically translate this high-level code to executable Python code, and it can then be used to run the simulation with the ARIAC environment that is based on the gazebo simulation. We encourage interested audience to read our paper and the references within to better understand our method. So with our prototype compilation and simulation framework, you can simulate the system with different layouts. And we can collect and monitor the simulation runs with very fine-grained details. In this slide, we show that we can keep track of the positions of 2 batteries and the sensors in real time. And then we can use the information to plot the 2D trajectories of the batteries and the sensors on the right. We also collect system level analytics, such as the throughput of the system. In table 1, we calculate the throughput by finding the average time to finish one order. And we consider 3 different layouts in combination with 3 different parameter values. The 3 layouts are as follows. The default layout is directly from the ARIAC environment. The space layout is increasing the space between robot models to ensure safer operations. And the last AGV layout use only half number of AGVs compared to the default layout. And then you'll be able to reduce the overall cost. So the capacity of AGV here means that the maximum number of product parts loaded on the AGV in each trip from the conveyor belt to the assembly stations. And observing this table, we can see that there's really no clear trend in the combination of layouts and the capacity parameters. For example, in each row, increasing the capacity helps the default and space layout, but not for the less AGV layout. And another example is that using less AGV with capacity 4, it is really comparable with the default layout. But when it is with capacity 8, the performance suddenly drops significantly. So this actually shows that we really need to be able to automatically generate simulation runs under various combinations of parameters and the layouts, floor plan layouts, and in order to search for the optimal design parameters. So in summary, we propose an approach to automatically generate simulators for different floor plan layouts, and we implement a prototype with preliminary experiments that can compare the performance of the system under different, and then can also be used for detailed runtime monitoring. And our approach is enabled by our formal model using parameterized automata and our previous work to translate these high-level state machine to Python call, executable Python code with shared variables. And this allows compositional design for the coordination software layer. Finally, I would like to thank the students work on the project, Daniel and Yubin, and my advisor, Professor Mitra, and also our collaborators from the University of Michigan. They gave us many valuable suggestions. Our code for the modified area simulation environment is available on GitHub, and you can reach out to me through my email here. This project is also funded by the NSF. Thank you for listening.